What's up, folks? So today we're going to do the inference portion of the joint model. It's going to be a very simple inference where both the image and the text share the same time step, and then we flow the noise to an image and a generated sample. So for the inference portion, we're just going to pass in a noisy image and a noisy text, and in latent space. So I guess this diagram isn't accurate if we're going to be talking about inference, right? Because we're not going to send the text to the FLAN encoder, right? So we're going to assume the text is in latent space and the image is in pixel space, and that the noisy text is in latent space and the noisy text is in image space, right? So it's going to be the same dimensions and as the latent space, and then we're going to send it through. We're going to essentially just continuously update these noisy latents with the velocity, and to produce a noisy latent to produce a latent text and a pixel in an image in pixel space. And then we're going to send the latent text that we generate through the decoder, the FLAN T5 decoder, and it's going to auto-aggressively generate a caption. So also, as part of this video, I need to fix the time portion of UNet, because I didn't end up coding that yet. So I need to fuse the image time and the text time together and send it through concatenate them and send it through a projection layer to make one fused timestep embedding. And that's the timestep embedding I'm going to use throughout the network. So there is more complex inference we can do where, you start with an image, a fully generated image, like you just pull an image and then you reshape it to make sure it's in the shape that the network expects. So it can be an image of whatever, and then you flow a noisy text embedding towards a generated sample, right? And then the generated sample will match the image, right? So that's one of the benefits of the joint model, but we're not going to do that. I just want to give you an idea of what inference looks like. So, okay. So we're here to do change in inference using change inference to generate text image. So we'll navigate here and we'll So we'll navigate here. Actually, I can probably just copy inference. We'll just call it inference joint. Inference joint. So we need to take in the encoder decoder, the FLAN T5 encoder and decoder, and then sequence length. That's the number of text tokens, the default number of text tokens that we're using for this model. You can see here, when we're defining the tokenizer, we're giving it a max length of 77, so that's what it's going to be. So, yeah, this looks good. So this is the inference from our standalone image model. Right, so now we just need to add the text portion, right? So we're gonna change this to X image, and then we need an X text. L is the dimension I'm using for sequence length, so L and P is what I've been using. Is it L and P? Have I been using L and P? Cross attention. Oh, P I've been using for image tokens, L, and we'll just say text dim. So sequence length. And right, and then encoder decoder dot hidden state. We can call this D. Okay. And then our encoder decoder, let's just type it so it makes it easier to code. Right, so this should be a instance class variable. Yep. So hidden state, I'm just setting it here to make it easy to grab in the inference. So this is just the dimensions of the embedding space of flan T5, right? Of T5. This is the size of the token, the text token. This is the size of the text tokens, right? Oh. Okay, so we have our image, we have our text, we have our lin space, we have our DT, so okay. It's extract something instead of making it all on one line. So this is our time. So, okay, let's go to our model. Okay, so our model takes in image, text, T image, T text, right? And see, T text is never being used. That's what I'm saying. I need to fix that, but I will after I do this inference. So T image, we're gonna make both time steps the same, right? Image, text, T image, T text, and this is gonna give us V image, V text, image text, right? Okay. And then V image, text. It's gonna be caption. Okay, I think this is all correct. This looks good. I never passed in the attention mask. Cross attention should have a default, yeah, attention mask none. So I'll need to attention mask. We're gonna say it's valid for all positions, right? So we're just gonna give it a ones, and it's gonna be B, L, D, D type. We have to give it a D type, torch.long, and then a device, okay. Okay, so that's good. We like that. And then caption, right? So now that once we've performed inference and we have our text latent, we're gonna pass to the flan T5 decoder. So encoder decoder dot decode, right? That's why I typed it, so I could just see encoder hidden states. Oh. Encoder hidden states xtxt. What's going on? Spinning. My processor is working heavy right now, probably because OBS is running. There you go. Encoder hidden states, max new tokens, sequence length, num beams, num. Did I pass that in? I didn't. We'll just make it 4. So this is for beam search. Sequence length 77. Or I don't know, we could say 32. We can say 32. Keep the caption small. I mean, they're not going to be detailed anyways. I mean, the results aren't great, but like even if they were pretty good, I mean, it's a global, the caption is like a, remember the text velocity head is simply passing in a global image context, right? These pooled features, and then it's concatenating them with the text tokens and sending them through a projection layer. So at the most, we're just going to get words that say what's in the object. It's not going to be any kind of great description, right? Okay, so this is inference. Now we need to go to UNet and we need to fix our time. So we have this T image. So this is we'll just say it's time embed image. Time embed text. Right, we can just do this, make it really simple. And then we'll say T embed is use torch.cat T so T embed right, it's just timed in B, so this is gonna be B timed in as well. So we're just gonna create this time fuse. standard pattern, which is just linear, which is going to be time embed it's going to be 2 times time dim time hit. We'll just say, I don't know. What's time dim? 128. So we'll just say 256. So we'll go 512. Okay, cool. So there's our projection layer. So if we run this, boom, boom, boom. Okay, good. So now time embedding is a fusion of both time contexts of the image and the text. So no matter, it's going to see a bunch of different time skip. It's going to see images and texts corrupted on a bunch of different time schedules, right? And it's just going to fuse them together and pass that context to the remainder of the network. Okay, so yeah, it's all good. Now, let's see. Inference peak number. Let's go to our config file. Where are we? Let's place a breakpoint here and then hit continue. Inference peak number is 1. So it should, move that. Far past that. Okay. Yep. Okay. We're doing do inference to do inference is false. See, I knew something was up. It's okay. Oh, and then I also never switched it out here. Inference, joint, encoder, decoder, batch size, sequence length. Okay, the breakpoint is hit. Good. So continue, it should hit in there. Okay. Attention mask isn't used. Need to pass it in, but yeah, it looks good. X text. Let's pass attention mask in. And also let's pass attention mask in. Oh, it's being passed in. Nice. Okay, that means it's being used. Okay. All right. Let's run it instead of debug it. I think we should see the TQDM loop. So image X caption. Samples, captions. Let's print captions. Should be strings. Okay, let's run this. Well, it should be tqdm.write. I think I'm getting sick. Wait a minute. Tension mask. Oh, I know what the problem is. The attention mask doesn't have tokens. It doesn't have an embedding for the tokens, right? So attention mask should be this. That's the problem. That is the problem. Let's just run it again without the debugger. Should work. Okay, so I reduced the number of steps. Base model output. Encoder hidden states. Base model output. Last hidden state or hidden states. It should be last hidden state. We want the last hidden state to be the encoder hidden states. Okay. Let's run this one more time. Okay, performing inference. It's going to be complete noise, of course, but and the text is going to be gibberish. Argument must be a string, not a list. Yeah. So it has 4 captions. They're all garbage. Oh, the local visualization. The flag for local visualization is false, so it's not going to show the images. But you know, just like before, they're just going to be noisy images. So that's inference. So it works. Our inference works great. And then we also fixed the. We also created a fuse, the timestep embedding for our UNet. All right, so this is that's, you know, this is our joint flow. I mean, this is our joint flow model. We've implemented the full thing. Next, I'll do a video to talk about the results that I got when I deployed it and trained it. Okay, thanks for watching.